All right, we are recording. Let's see here. I won't take attendance yet. I'll just do the repetitive announcements and reminders that I've been saying for a long time, so let's just say them again. You can still meet me online for exam 1. I can give you all the correct answers, which you'll need to study for the final exam. And in addition to getting all the correct answers, I will boost your grade for that exam by 5%. Any questions about that? All right, you can still retake exam 2 until November 9th. Retake it as many times as you want. There's nothing to lose. Once you're done, just email me and I will average your first grade and your highest grade. Again, nothing to lose. It's also good practice for the final exam. Exam 3 will be due on November 9th, the same date that exam 2 retake will be over. And then the final exam, I looked it up, as I talked about it on Monday, so I looked it up. It will be in this room from 8 to 9:50 on December 8th. So make sure you're here. But again, I realize how stressful finals week is, so if that doesn't work for you, I might be able to work around it, right? So just email me. You know, again, for example, if you have the biggest, hardest exam that you can think of on Monday at 11 o'clock, and you'd rather just wait and like do that, you know, mine later in the week, maybe we can make some arrangements. We'll probably have to meet online. But anyway, the point is, this is officially when we're taking it. And if I don't hear anything from you, that's when you should be here. And there's going to be a password to get into the final exam. You won't be able to have the password unless you're in here. So anyway, any questions about the final exams or exams at all? All right, again, to remind you, I'm here to help you for, well, whenever you want, but you're always guaranteed to find me in my office and online for office hours. And from today, they're from 11 to 2. All right, it's 8:01. Any questions about office hours? All right. I'll remind you again to make sure you check your course announcements and your emails before you come in every day, especially if you're a commuter, because it's not an emergency and I might not be able to come in which case I will post an announcement and then you should get an automatic email at WVSU showing that I posted that announcement. You're like, okay, I know I'm not coming in. So make sure you do that. Speaking of which, just in case that does happen, and also because it's my birthday, on November 10th, we will not meet in person. It's going to be a meeting online only. Sometime between now and then, I'm going to send you the link. Some people already have the link, but the reason I'm not sending it yet is that sometimes those links stop working. So perhaps the one that we're using at the moment might not be working by then. So I'm going to wait till we're a little bit closer and then send you the link. All you have to do is click the link and you can join us online. So any questions about November 10th? All right. Also, not just the lecture, but also office hours are going to be online as well. So anyway, just a reminder too, today's lab is in person. Hasn't been like that for a couple of weeks. So if you have not turned the completed lab in, not just the pre-lab, but the whole lab, then you need to be here this week. But next week it is virtual. So we're going kind of back to normal next week. So that means there's no pre-lab for next week, if I remember correctly. And you don't need to be here next week. I will be here next week if you need me, but you don't have to come. So any questions about labs? All right, once again, attendance is mandatory. You have to be here. I have to turn it in to the college, to the university. And I grade you on participation. So if you're here in person right now, you need to write down all the words, all the attendance words that I say. And then at the end of it, email those to me. In addition to one question about material covered in the lecture. That's all you need to do, right? Make sure you get those in by 9 a.m. If you're live, like right now, streaming with us, the same goes for you. And of course, if you're watching this video at a later date, instead of just writing down the attendance words, you also need to take screenshots. So any questions about the course announcements or reminders? All right, let's go ahead and take attendance. Brumfeld is here. Champion is here. Gross is online. Gunther is here. Both Hills are here. Jackson is not here. Pease is here. Perez is not here. Sigmund is not here. Madison is not, or Slaughter is not here. Smith is here. Stover is here. Tompkins is not here. The Nest is not here. Watson, I think, is online. Young is not here. Swyback is here. Lawrence is not here. Wilson is not here. Did I miss anybody? All right. Anyway, the first word for attendance, this little picture right here might be hard to see, but the first word for attendance is stress. Yeah, Recruit is probably pretty stressed because he's getting screamed at by a drill instructor. But today is National Stress Awareness Day, so there you go. First word for attendance. That being said, let's jump back into this chapter about evolution and the different types of evolution. So this is where we left off. We left off talking about Darwin's trip around the world, specifically when he was some of his observations about South America, right? So we talked about how he was comparing living things that he found in South America to living things that he found everywhere. He was also comparing fossils that he found in South America, so things that are no longer living, to things that were living, right? He saw a lot of similarities. That's where we left off. That's an old slide. Here's the first new slide. Darwin was intrigued by the distribution of organisms on the Galapagos Islands. So I mentioned these islands earlier, and I talked about how their size and shape and vicinity to South America is not trivial. It's actually pretty important, which is why I'm bringing it up again, giving you these numbers. Not that I'm going to ask you these numbers, but there's some important things to note. These islands are relatively young, right? So they're volcanic islands, meaning for a while there, they just didn't exist, right? As far as the age of the Earth is concerned, they are new islands, right? They were created with volcanoes. And they're also about 500 miles, 540 miles off the South American coast. And like I said on Monday, that's relevant because it's far enough away where life can't just easily leave South America and go to the Galapagos Islands, right? There's not a lot of life going back and forth between those two spots, the mainland and the islands. But it is close enough to where it can happen occasionally, on very rare occasions. Like, again, maybe some birds get caught up in a storm and they can't land anywhere until the storm goes away. The storm happens to bring them to the Galapagos, and there you go, right? So it's the sweet spot, far enough away to where things aren't going back and forth a lot, mixing up the genes, but close enough where they can happen every once in a while. So because of this, most animals that you find on the Galapagos Islands are found nowhere else in the world. But despite being completely unique, they do at least resemble some of the animals that, and plants too, they don't mention that, but it does resemble the life that comes from South America, which again is because of this perfect little spot, right? So we know life has come from South America occasionally and made it to the islands. But it happens rarely, and because of that, there's been a lot of change, and now we have these completely unique organisms. This is all just an introduction. There's nothing on that slide that's going to be important for the exam, but are there any questions about that slide? All right. Here's some more stuff, just some examples that I'm not going to test you on. But he noticed that the Galapagos marine iguanas had flattened tails that helped them swim, right? So he'd been all over the world. He'd seen lizards, all types of lizards from all over the world. He'd been to South America and seen the iguanas there. But then finally he got to the Galapagos Islands and noticed, wow, I know it's hard to see in those pictures, but these iguanas are clearly iguanas. They're definitely related to the iguanas that he was used to seeing. But they were also unique in their own ways. Like they had all these things that helped them live in the water, which is not what he was used to seeing. He was used to seeing iguanas live in trees. But here on these islands, they were adapted to live in the water. He also noticed that each island had a very distinct shell, or excuse me, each island had its own turtle species with a very distinct shell. And again, that goes back to what I was saying up here. Well, you can't really see it in that picture. But the other picture, if you can remember, it showed the Galapagos Islands, and there was a bunch of them. So amongst all those islands, all the iguanas are the same, right? Because those are marine iguanas. They can easily get from island to island. But the tortoises are completely different depending on the island, which makes sense because those big old things are not going to be able to just swim from island to island. So if you have a population of tortoises on one island with one environment, and then a population of tortoises on another island with a completely different environment, obviously they're going to grow and evolve to be slightly different, or in this case, pretty big differences with the shells. But again, those are just examples. I'm not going to ask you anything about it. Are there any questions about that slide? All right, let me double check here. Yeah, so if you download no, never mind. I was about to say those are not videos, but here we go. If you download the PowerPoint, you can watch these little videos. There's a really good documentary with David Attenborough. I'll try to find that and share it with you. But it gives you a lot of great information about this. But here's another example. Here's a dome shell tortoise from one of the islands. I forget which one. It doesn't matter. And here's a saddleback shell tortoise from a different island. And again, it's not important. I'm not going to ask you which one, but there's great examples of how life on these islands are different because of the different environments, which is the whole point of what we're saying about natural selection, right? Your environment is going to change populations. All right, so any questions so far? All right, the next word for attendance is art. as in Art Garfunkel. Today is his birthday. But anyway, going back to talking about Darwin and his journey, we were done talking about his observations, right? We've kind of explained the important stuff of what he saw. And now we're talking about his new insights, right? So him reflecting back on all of his observations. What did he come up with? But before we mention that, it's also worth noting that when he was on that trip, right, he was reading a book, probably reading a lot of books, but he got very influenced by one of them. It's called Principles of Geology by this guy named Charles Lyell. I'm not going to ask you anything about that book or that author, but I'll give you the information anyway. If you click that link, you can get, I think, a little documentary about him, if I remember correctly. Yep, it's a little YouTube video about him. Anyway, in this book, this guy said that the Earth was ancient. And remember, back then, a lot of people maintained that the Earth was, I think, 5,000 years, 5,000 years old, it said. So that's still relatively new information. He also said that the Earth was sculpted over millions of years by gradual geological processes that continue today. And again, I think on Monday I talked about the mountains, right? Even where we live, that's a great example, because they used to be the highest mountains in the world due to geological processes, gradual ones, right? When the continents are colliding, our mountains grew. And then the continents stopped colliding, and then you had glaciers, for example, come down and basically flatten our mountains, basically. Meanwhile, and again, this is not important, these are just good examples. The Himalayas, right? Hopefully you know the tallest mountain in the world is Mount Everest. And it's still growing because that South America, that Indian continent is still crashing into the Asian continent, and that's what's causing it to grow. So anyway, yeah, he was on his trip. He's influenced by this book. This is relatively new thinking for him and for science in general. And he also witnessed the power of natural forces to change Earth's surface, right? So he went through an earthquake, at least one. And in that earthquake, he saw that the rocks on there had risen by a meter, 3 feet, which might not sound like much, but when you think about it, it's like from here to here, almost, maybe about like that. Imagine just seeing, 1 minute something's down there, and the next minute it's 3 feet taller, and then thinking about how the Earth is actually millions of years old. But then you put those two things together, like, all right, if the world can change that much in an instant, then how much change can we see over millions of years? So it's not always gradual, like that bullet point says, but sometimes it can be pretty drastic. So because of all this, he began to doubt that the Earth and all of its organisms had been created only a few thousand years earlier. So remember back where we were I was giving you the history of thought, basically. I said that was the prevailing thought at the time, was that the world was only a few thousand years old, and that every species that you see on Earth has been here always and always will be, and there's never been any extinctions, and none of these species have changed. That's what people thought mostly back then. And he started, because of all this, having serious doubts. That was during his trip. Then finally he got back to England, right? So he spent years and years reflecting on his observations. He analyzed his specimen collection, right? He was reading his notes. So it's not like he went on his trip and he got back and was like, all right, that was fun, I'm done with that. But he reflected on it, learned a lot from it. He discussed his works with his colleagues. There's a whole documentary about that too. Hopefully that might be already embedded in the natural selection lab. But there's one, it's not a documentary, almost like a more dramatized. It's more like a movie, but it's worth watching. Anyway, still while he's in England and reflecting upon all of his work, he concluded that present-day species are descendants of ancient ancestors, which they still resemble in some ways. And again, that was the big thing right there, right? That was a new thought. Of course, you know that Lamarck also mentions sort of the same thing about species evolving. So in a sense, that necessarily wasn't new. But yes, that's what he started to think, right? So he's looking at life that's living now. He's looked at all these fossils. He's looked at all the different living things and how they're similar and different, comparing it to the dead things and how similar and different they are. And that's what he concluded, right? The life that we see right now, or back then, all those species, all that life is descendants of ancestors. But over time, differences gradually accumulated by a process he called descent with modification. It's very easy to see in humans, right? You look at a mom and a dad, and generally speaking, kid is usually kind of a mixture, or the kid's multiple if there's more than one kid. It's like a mixture of the two, right? So they're always a little bit different, very rarely. I mean, sometimes you'll see a kid that looks a lot like the mom or the dad, but even then, they're still not exactly. So again, for each generation, there are slight differences. Now in nature, as opposed to usually with humans, those modifications might give you an advantage or a disadvantage. So even within one family, right? Like if you just think of, I don't know, a lion and its cubs, right? Even amongst that genetic diversity, amongst that one litter of cubs, some of them are going to be more equipped to live in that environment. Some of them are going to be a little bit less equipped. Therefore, the chances of one reproducing successfully is a little bit higher than the other one reproducing successfully. So yeah, these are all his new insights. He also proposed that the mechanism for how life evolves, remember that's where it gets a little bit new, because he wasn't the first person to say that life evolved. Lamarck also said that. But he correctly figured out one of the mechanisms anyway, which is natural selection. And that's the big one. That's the one we're going to talk about the most. But again, before I move forward, I want to point out that's not the only way that evolution happens. It's just the big way. Which is why that last question on the natural selection lab says it defends your answer, because strictly based on natural selection, the moth population should not change without predators. It's the predators that drove them, that the black was advantageous and white was not, because of the predators. Nothing else. There was no other advantage to being dark. There was no other reason that being white would be a disadvantage. It was only because of the predator. But that's why I said defend it, because again, there are other ways to evolve. So strictly based on natural selection, you would expect that there'd be no change. But later in this chapter, you're going to learn about the other ways that things evolve, and then you realize, okay, there may have been another way for them to evolve. Anyway, what is natural selection? I'm going to define it a few ways based on the old textbook and your new textbook, things like that. Here's the first definition. Individuals that have certain traits are more likely to survive and reproduce than individuals with other traits. It's that simple. I'm probably not going to ask you the definition of natural selection. I'm probably going to give you some examples of like, all right, what type of natural selection is this? You're going to learn there's different categories. And so we'll get there. But yeah, that's what natural selection is. Some people say it's a survival of the fittest. And I don't like that because that's too vague. That's on, not vague, it's not correct. It's not enough information, because surviving in itself is not enough for natural selection. So for example, there was some kind of, I don't know, let's go with the lions again, since I used that example already. If there was a lion and it had little baby lions, and one of them had some kind of mutation that just made it like the fastest lion ever, right? So it can outrun all of its prey, and it can outrun all of its foes, and it can beat all the other lions when it's having territorial disputes, right? That would make it a very successful lion. But if the same mutation that caused that also caused it to be infertile, and as far as natural selection is concerned, that's completely useless. Because yeah, that thing might have a survival advantage, but if it can't pass along those genes, and as far as natural selection is concerned, it's nothing. Anyway, any questions about that slide? All right, so we're still talking about his new insights. He hypothesizes that descendants of remote ancestors spread into various habitats over millions and millions of years, that natural selection resulted in diverse modifications or evolutionary adaptations that fit them to specific ways of life in their environment. So again, just natural selection, right? He's in his idea, like he's trying to describe how natural selection has resulted in what we see today. Which is not always the case too. I'll also mention that, right? So things are now still currently evolving through natural selection. Natural selection is not a process that just stopped. It's still going on today. There's still evidence of it happening today. It's just not always as drastic as forming a new species. I think usually, unfortunately, people get that stuck in their head. So it's a good time to remind you of that too. When we're talking about natural selection, yes, especially in this context, we are talking about forming new species. But natural selection does not always result in new species. Sometimes just a species changes, but it's still the same species. The peppered moths, for example, right? That was a great example of natural selection, but it's still the same species. That one species, as you know, had 3 different variations. It just happened that one of those variations was then overtook due to natural selection, but it was still the same species. Anyway, any questions about that slide? All right, next word for attendance. Donuts. It's National Donut Day. So now that we've kind of got Darwin's background, right, kind of know what he did, what he observed on his trip, what he came up with after he was reflecting on it, now finally we can really get into his theory, which is the stuff that you need to know. So again, this was a very long process. It's not like he just went on one trip and said, oh yeah, he came up with this whole book right away. Life evolves, I'm done, right? He spent decades working on this. Right? He spent 2 decades after he got back compiling and writing about evidence for evolution. I'm not going to ask you that. You don't even know how long it took him, not for the exam anyway, but it is worth noting, right? It's not like he just came up with this on a whim. Meanwhile, like I mentioned on Monday, there was a guy I was going to tell you about, so I'm telling you about him right now. This guy named Alfred Russel Wallace. If you click that link, you can watch a little YouTube video about him. He came up with similar conclusions. And it's interesting, too, because he was also a British naturalist. He was also doing field work, and it's interesting. There's Indonesia, and obviously that's no Galapagos Islands, but some of the interesting stuff to me about this is, you got bigger islands and smaller islands. So, right, all these different islands with all these different little environments, just like the Galapagos. Indonesia is far enough away from mainland Australia and mainland Europe that it's probably hard for life to get onto those islands. But close enough to where it's not impossible. So it does happen occasionally, just like the Galapagos Islands, right? So he was in similar situations and came up with an almost identical theory. And again, if you download that, or if you click that link, you can watch a little video about it. But as far as the exam is concerned, that's a very unimportant slide. Any questions? Okay. So again, the big book that we talked about, he wrote more than one, but the one that made him famous is On the Origins of Species by Means of Natural Selection. And that book made 2 big proposals. First of all, existing species descended from ancestral species. So we'll stop at that one for now. That's the big one because I think that's what people mostly argue about. The people who are against evolution or natural selection, I think that's what they're actually against. Because again, there's evidence that evolution is happening right now, right? Antibiotic resistance, that's natural selection. That's one great example. It's happening. We see it happening. Somebody wrote a question on one of those attendance words about viruses evolving, and that's a great example too. Yeah, viruses evolve. Things are evolving, right? But again, my point here is, even if you don't agree that that's how life came to be, even if you agree God just said, all right, I made a human, right? Even if that's your belief, then the other bullet point is the one I guess you should at least accept that, right? Natural selection is the mechanism for evolution. So again, even if you don't believe that's how things were made, we know it's a fact. It's just a fact that it's happening now. Of course, there's evidence too that that's how it was made, but I'm not here to try to change your beliefs. Any questions about this slide? And this is again a very unimportant slide as far as the exam is concerned. This is still kind of like telling you the story. All right. Also, I want to point out once again that even though he proposed that natural selection was the mechanism for evolution, as you're going to learn later, there are other mechanisms for evolution. That's just the big one. So the idea that evolution generated, the idea of evolution that he came up with, his theory, has generated predictions that have been tested and verified by over 150 years of research, right? So this is why it's a theory now. It's not a hypothesis. You remember back when we started in chapter 1, we talked about the differences and the relationships between theories and hypotheses. Theories are basically they're almost like fact, right? And that's a great example of why, right? Over 150 years of research. Based on the theory of natural selection, we can make predictions. Also, speaking of that lab, that's a question a lot of people got wrong. How do you test theories? You don't just make predictions based on theories. Then you have to go see if your experiments give you the results that you expected, right? So, for example, if I say, based on the theory of natural selection, I think the average human will be 7'2" in 100 years. I just made a theory I just made a prediction based on the theory of natural selection. Did I just test natural selection by making that theory or prediction? No, I just made a prediction, right? So making predictions is only half of it. Sorry, got off on a tangent. But these are good hints. So if you got that question wrong, as always, you can always resubmit things with corrections to help you grade. Anyway, consequently, scientists regard evolution by means of natural selection as a theory, right? So widely explanatory idea. It's broader in scope than a hypothesis. It supports or generates new hypotheses, right? All the stuff we talked about way back in chapter 1. We're just kind of saying it again. Yeah. So any questions about the theory of natural selection or a theory in general? All right, that brings us to the theory of evolution. So remember, natural selection and evolution, those words are not necessarily interchangeable, because natural selection is just one way that life evolves. So the theory of evolution states that living species are descendants of ancestral species that were different from present day ones. And I did not make this meme. I don't make any of them. I just find them and put them into the PowerPoints. But that would be a good test question. If I were to show you that picture, say, what kind of evolution is this? Lamarckism, Darwinism. Actually, that would be the only two options. But if you remember what I was saying about Lamarck, even though it's just a joke, Lamarck said if you used something, that's how it was passed along. Like, again, the real example of the giraffe. He thought giraffes had long necks because they were stretching them their whole lives. Therefore, when they had offsprings, their necks were also stretched, and then their offsprings would be a little bit more stretched. So based on that, and plus no one really does it anymore, but that's making fun of duck face. The duck face selfie. Your generation doesn't do that, right? I think that was a generation before you guys. I haven't seen it as much. You guys have more of the fish lips, where you're going like, like kind of gaping your mouth a little bit, eating that like that. No judgment. One day you'll look back on it. Anyway, that's the theory of evolution. Any questions about that? All right, nice and easy. So now we'll talk about this. As far as the exam is concerned, we're about to start getting into some more important stuff here. Now we're talking about some evidence of evolution. Not as important as the stuff that's going to come after that, as far as the exam is concerned, but it's more important than the stuff we talked about before that, as far as the exam is concerned. So all the stuff I've talked about previously, that's important for you to understand what I'm going to end up teaching you. But as far as the exam is concerned, again, very few questions about that. The next word for attendance is also up there. It's kind of hard to see. I don't know if anybody can guess. There's a couple ways you could go with that. Now you can't see it. I'm not going to ask anybody to guess. The next word for attendance is redhead. Or even red hair. Or even just give me the name of a redheaded person that you know. I don't care. It's one of those things. One of those three. Whichever you want. I think today is National Appreciate Your Red Hair Day, something like that. And of course, since the Marine Corps birthday is coming up, I actually chose a Marine who was redheaded for that picture. Anyway, let's talk about the evolution. Excuse me, the evidence. And once again, I want to point this out like I did on Monday. There's entire classes on evolution, right? We're spending one chapter talking about evolution. But there's entire college courses where you talk about evolution. And very often, not even 100 level college courses. We're talking like 300 level, 400, like complicated classes that spend an entire semester studying this one topic. So, I just want to point out again, what we're doing here is scratching the surface. I don't have time to give you all the evidence of evolution. Certainly don't have time to talk about the alternatives. Again, like when trying to be fair, where people say, okay, that you say this is how life was created. Why don't you talk about all these other versions, these other ideas of how life is created? And I tell you why, because we don't have time. We've got the one chapter to talk about this, and there's thousands of different explanations, not scientific, but other explanations of how life got here. So that's why we don't talk about it. Let's jump into the evidence of evolution. Evolution leaves observable signs. That's why I got a picture of that sign right there. And if you download the PowerPoint and click that, then that video is about, it's actually a link to a video. You know what? It's a video, but I don't remember specifically what it's about. Obviously the evidence of evolution, but I don't know if it's broad or if it's about fossils or whatever. But you can click it and watch it if you want. This is a separate link for a separate video. You can watch all that. As you might imagine, there's a lot of videos on evolution. But anyway, where are we finding these signs? We find them in fossils, which we're going to talk about specifically, right? We're going to go into more detail about that. We find evidence of evolution in today's organisms, even humans. I'm going to give some good examples for humans, like how you can see how we've evolved. And evolution doesn't always mean necessarily it works out in a good way. Sometimes evolution not so good. And you'll see what I mean by that when we talk about the evidence in today's organism. Anyway, so we're going to talk about these things separately. This slide is merely an introduction to what we're about to talk about. So I won't even take questions. We'll just move forward. Let's talk about the evolution from fossils first. Before we talk about the evolution of fossils, we need to talk about what fossils are, in case you don't know. Fossils document differences between past and present organisms. That doesn't really say what they are. That just says how they're useful in this conversation. Right? So what do we care about fossils? Well, in the context of this conversation, this helps us compare and contrast living things with extinct things, right? And it shows, obviously, because of that many species have become extinct. So we have fossil records. We see these fossils that show these organisms used to exist and no longer exist. Again, back in the day, that was a big thing. And we can see how those things that used to exist that no longer exist must have been ancestors of some of these things that currently exist because there's similarities. We should also point out the soft parts of organisms decay rapidly. So usually fossils are made up of the hard parts that are rich in minerals, right? So that's why you'll find fossilized shark teeth at the beach, or sometimes in creeks in the middle of Florida. We used to go shark hunting in Gainesville, Florida, in the middle of the state. You go in the creeks and find shark teeth. But anyway, it's the hard parts, right? So I think most people, when they think of fossils, they probably think of big like T-Rex skeletons. And that's a great example of a type of fossil because that T-Rex died. His bone was made, it's hard, it was made of minerals, it didn't really decompose. So instead it was fossilized and basically turned into stone. Any questions so far? All right, so again, I think that's what most people think of as fossils, like the big T-Rex skeletons. But this is where I want to make sure you're aware of this. Not all fossils are actual remnants, right? So it's not always a skeleton or an egg, right? Sometimes it's a cast. You might need to know what a cast is for the exam. A cast is a buried organism that has been decomposed and leaves an empty mold filled by minerals dissolved in water. So in that case, the thing did completely decompose and it used the word disappear, right? Because nothing is created or destroyed, but for all intents and purposes, it disappeared. But again, it left a mold. So it died. There was probably some mud around it. That mud got dried and turned hard. Eventually that mud turned to stone, and now you get to see this perfect little imprint. For extra credit for any of this, just like for one quick, easy point, no, don't do it now. As a matter of fact, I'll give you 0 points if you do it now. If I prefer right now, you pay attention to the lecture. But sometime later in the week, if you send me a picture of a cast, and be like, all right, here's an example of a cast. This was this type of animal. Here's the link to my source. Nice and simple, right? Nice one point of extra credit. Same thing with an imprint. An imprint is another type of fossil. That kind of just says what it is, right? Footprints, burrows, whatever. So it's the same situation as a cast in that a living thing changed basically probably mud, and then that left an imprint, and then that turned to stone. But in this case, it wasn't the whole body that did it. It was just like that as a footprint. Or maybe where it used to live, maybe it burrowed a hole. There's again some good examples. So for extra credit, feel free to find me an example of an imprint. Let's make it a little bit more challenging. How about a recent example? I don't want to get so complicated. We're like, how recent? What do you consider recent? So obviously, if you send me something from 1976, that's not recent. There's been a lot of new casts found, a lot of new imprints. So just Google it, find it, send it to me, include the link, 1 point of extra credit. Then there's this one more. Coprolites. That's what that picture is down there. It's a little bit hard to see, but a coprolite is fossilized poop, basically. And if you click that picture on the bottom right of that fossilized poop, it's kind of funny. It's a video. It was a natural history museum, and the guy working there is walking around, passing around this coprolite. He's not telling them it's a coprolite at first. He just tells them it's a fossil because it is a fossil. And he's passing it around, and he's like, oh, cool, a fossil. And they're holding it, and then finally he's like, oh, let me tell you what kind of fossil it is. It's a coprolite. And he was like, what's that? He's like, it's poop. And some people are like, oh, gross. But anyway, yeah. So those are some examples of some fossils that are not necessarily, remains of an organism. Could be remains of their poop, or remains of where they stepped or lived, or remains of where they died, and then that imprint became stone. Anyway, another word you might need to know for the exam, and I'm pretty sure you guys already know this, paleontologist. Right? These are scientists who study fossils. Next to movies like Jurassic Park that most people are very familiar with paleontologist is. Or, like in the first Jurassic Park, if you get very specific, there's different types of paleontologists, right? So I forget the character's name, but she was a paleobotanist, right? So she studied fossils, but she was focused on the plants back in the day. Anyway, any questions about this slide? Okay. Rarely, entire organisms, including the soft parts, right? So soft parts aren't usually fossilized, but sometimes it does happen. Sometimes the entire organism is encased in a medium that prevents decomposition. Again, going back to the Jurassic Park example, insect and amber. So if you remember, that's where they got the DNA. I'm trying to remember how they said it in the movie, the dinosaur DNA, doing that little tour they did. But anyway, there was that mosquito that landed on a tree that was then covered in sap that perfectly preserved it. That sap eventually turned into stone, i.e. amber, and they were able to drill in there and get some of the dinosaur blood out of it. But anyway, that's one example. Another example, and again, you can look any of these up for extra credit. There's been mammoths that have been found in ice, bison, even some humans. So if you click on that link, I think that's another video of a recent find where they found a human. Yeah, it's a little YouTube video. I think that was one that was preserved in a bog instead of frozen ice. But obviously, that picture is not an actual human preserved in ice. That's just from a movie. Anyway, any questions about that slide? The next slide I'm going to show you is a picture from the old textbook that kind of summarizes everything we've talked about so far, all these different types of fossils. Okay, so here's a petrified wood. That's a great example. So far, mostly what we've been talking about is animals, but it's not always animals that we're dealing with when we're dealing with fossils. So a tree dies, if it gets preserved the right way, eventually it might turn to stone, and that's what petrified wood is, right? Here you have a footprint. You can see these footprints. That's an example of a fossil, right? The animal's not there, but you can see where it was. There's evidence of that animal existing. Here's the other thing I was talking about with the amber, right? So you have the mosquito attracting the amber. Here's what most people probably think about when they think of fossils. So just a bone, right? In that case, a dinosaur bone. And of course, like I said, sometimes an entire organism is frozen and preserved, and that's what that is. As a matter of fact, I don't know this for sure. It's been a while since I've heard about it, but I know they talked about resurrecting an extinct species, a direwolf. And I don't remember the details. I would assume they got the DNA from the direwolf to resurrect it from a frozen specimen, but I don't know for sure. You can look it up. I know they're talking about bringing back mammoths, and I know that that's where they're talking about getting the DNA from, is from a specimen that was found frozen. But all stuff you can look into for extra credit. Any questions so far? Okay, let's talk about the fossil record. Now I wish I knew more about geology, because this would be a lot more interesting. Not this lecture. Nothing we can do about that. But the fossil record in itself would be more interesting if you knew geology. But I don't know that much of it. But even without knowing geology, we can know the basics, right? Let's talk about it. The fossil record is the sequence of fossils as they appear in rock layers marking the passage of geological time. So this picture was taken off of I-64. I'm sure you've seen places like it, even if you haven't been to that exact spot, and it might be a little bit hard to see, but there's lines in the rock, right? And that is the passage of geological time. Now, even though I'm not a geologist, and I wish I knew more, because a geologist could probably look at this picture and be like, oh yeah, that was the Carboniferous era, right? They could probably tell by looking and tell you when it was and what Earth was like at that time, but I don't know that. Here's what I do know, and here's what you know. This is common sense. I mean, well, maybe it's not that common. Obviously, this used to be like that. Geological things have happened, and it's kind of made it like this. But this is the top, right? And then this is deeper, 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 deeper. So this is young stuff. This is old stuff. So even without knowing all the different eras and knowing what the geologist might, if you found a fossil, this might be a good test question too. Let's say you were just looking for fossils here, and you found fossils right here at site A, and then you also found fossils right here at site B, and then you also found a fossil right here at site C. And this will be a good test question. And I said, which one of those fossils is the oldest? Which came first? And the answer would be C, right? Because this is the top, right? This is what used to be the top, and this is years, years, and years, and years, and there's the bottom. So C would be older than B, which would be older than A. So again, without even knowing the exact dates, you could at least say, especially if these organisms appear to be related to each other in the fossils, you could say logically that B must have been descended from C and A must have been descended from B. Because chronologically, it would have just had to have happened that way. So any questions about the fossil record? All right. So this is also important to note. The fossil record is not perfect. Even Darwin acknowledged the fossil record is incomplete. So why is that? Because this is a big argument. A lot of people argue like, all right, if you're saying this thing is related to this thing, and they look so different, then where's the organism that lived between them? Right? But not all organisms lived in an area that favored fossilization. Otherwise, there'd be a lot more fossils than there are. Right? You probably couldn't throw a stone without that stone being a fossil. There'd be a lot more fossils if that were the case, right? So fossilization was a relatively rare thing, so that's important to keep in mind. So when skeptics say, again, if this thing is related to this thing, and they're millions of years apart, then where's the in-between things? And that's one of the answers of why, right? Maybe they existed, or they must have existed, but they weren't fossilized. Another thing to point out, and I'm going off on a tangent again here, but people will make that argument, right? If this thing was related to this thing, I don't know, if A was related to Z, then where's anything in between? Like, where's the evidence that comes in between? And then someone will find something, but oh, I found something. I found this Q fossil, right? And now it's like, it really does close the gap between A and C. But then the critics will say, okay, well, if A is related to Q, then where's everything in between? And somebody eventually will come out with something like, oh, I found an F. So anyway, that's how it goes, right? The skeptics will always have that. Oh, well, if this thing is related to this thing, what about the in-between? And then we find the in-between, they'll say the same thing again. They'll move the goalposts, right? Well, what about the in-between between those? But anyway, yes, the fossil records are not complete. Not everything's lived in a place and time and a condition where it could be fossilized. Another important thing to note is that many fossils were in rocks that were later distorted or destroyed. So, you saw those pictures that I showed you off of I-64 that used to be flat, but then they had all these geological changes that make it change like that. I told you that the Himalaya mountains, the tallest mountains in the world currently, are happening because the Indian continent is crashing into the Asian continent. So obviously that's going to destroy the rock there, right? It's going to destroy possibly some fossils that would be found in that rock. And then it's also worth noting that, we haven't been all over the world yet. There's so many places where we haven't been, and so many places that we still can't even get to. So there might be some good fossils in between A and Z to prove that these things are related. But it might be possible that we just can't get to them. So again, that is very important to note, right? The fossil record is not perfect. Not everything can be fossilized. Sometimes those fossils have been destroyed. Sometimes we haven't even gotten to them yet. Maybe we will, maybe we won't. Any questions about that side? Okay. So, we'll skip this part. So once again, these these PowerPoints are based off of the old textbook. Every chapter of the old textbook had this called The Process of Science, where they brought up a real scientific study that was relevant to that chapter, which is really good because then you learn a little bit more about that chapter, and also it reinforces the idea of scientific method, which probably is more important than anything else for you guys since you're not majors. Scientific thinking and understanding how to do experiments and think scientifically and think critically, that's more important than you memorizing, how the scientific name goes, right? The binomial nomenclature. But anyway, because it's not important and because I'm not going to grade you on it, I'm going to skip past it. If you download the PowerPoint, you can look into it if you want. That's a long one. But it really basically talks about where whales came from. Long story short, there used to be land-dwelling mammals, and then they evolved, and they're back to the sea. Which is interesting because even though we're talking about evolution, we don't really talk about how life came to be. What we know now is that life started in the ocean. So eventually you had fish that had basically like limbs that were like a mudfish that you still see today that are almost like arms, or little arms and legs. And those things evolved to be amphibians, and then amphibians evolved to be reptiles, and then those evolved to be mammals. And then some of those mammals went right back to where it came from, and those land mammals evolved to be back in the sea. But anyway, We're done talking about evidence from fossils. That one's probably pretty easy. Let's talk about a subject that's a little bit more complicated, and it's called evidence from homologies. Does anybody even know what a homology is? That's okay, I didn't really expect anybody to. What's the prefix homo mean? Yeah, one and the same, similar, sure. So similarities resulting from common ancestry are known as homologies. That's what homologies are. Similarities from common ancestry, meaning they have that one thing in common, that thing that's the same, right? There's something that's the same. That's a homology. So characteristics of ancestral organisms that were altered over time as descendants face different environmental conditions. So the point is, like, you can, again, look at these old fossils and compare and contrast those organisms that no longer exist with organisms that do exist. And over time, you can see how things have changed. You can see, like, that bone started off this size, right? Maybe bone A was bigger and bone C was smaller. And then as time went on, A got smaller and B got bigger, whatever. The point is, over time, you can see it. You can see the changes. And then eventually, we get to where we're at today, and we can look at living things. We can compare and contrast all these things that are alive. And if we hypothesize that we have, 3 different species that descended from one ancestor species, then we can compare and contrast those living species that are alive today with what we're hypothesizing that their ancestral species was, and compare and contrast all 4. And you're doing that by looking at these homologies. Because related species can have characteristics that have underlying similarities, yet different functions. Here's a great example on that next slide. So I've got a picture here on this slide, but it's a little bit hard to see. The next picture is basically trying to show you the same thing, and it's a little bit easier to see. This is a great example, right? Humans, lizards, cats, whales, bats, frogs, birds. We are all tetrapods. We're all related in that way. Like I told you, started off as fish. Then fish also diverged, so obviously fish still exists, but then we have amphibians branch off from that, right? And then from amphibians, even though we still have amphibians, we had reptiles that branched off from that. And then from the reptiles, we have birds that branched off from reptiles, and we have animals that branched off from reptiles. So we have a common ancestor way back. And because of that, and again, the thing that makes us all in common is we're tetrapods, right? We have 4 limbs. But if you look, you can see obviously the difference between a human and a lizard and a cat and a whale and a bat and a frog and a bird, right? Our limbs have different purposes. A bird, their limb helps them fly. A whale's helps them swim, right? A cat helps them walk and kill prey. The humans doesn't do much for walking, but it's there to manipulate things, right? So you can look at all these different things, and you can look and see how they're similar. And we'll talk a little bit more about that. And again, there's a whole class about this, so we only get to scratch the surface. But there are similarities between, we've got this one big bone, and then the 2 smaller ones, and then you got wrist bones and finger bones, basically, right? And we all have that. Now, it's all a little bit different because it's changed over time, but we have these similarities, right? The one big bone, the 2 smaller ones, some version of the wrist bones, some version of the finger bones. Here's a better picture. This is from the old textbook. So it's not in your textbook, but there we go. So the human, right? You've got those 2 bones and wrist bones. Cats have the same 2 bones and wrist bone. Whales, same 2 bones, wrist bone. Bats, same 2 bones, wrist bone. Wrist bones. I keep saying bone like it's 1, but obviously it's not. And it's the same number in just different shape. Because again, we evolved differently from the same common ancestor. But as time went on, these organisms were facing different environments and doing different things with their limbs. They changed over time. And sometimes, your book doesn't get into this, I keep saying change over time, but sometimes there can be a mutation that's huge and just makes a huge change immediately. And if that huge change that happened immediately, like in 1 generation, if it's advantageous, obviously it's going to stick around, right? We know that from natural selection. And of course, I'm sure that much more often than that, there's been big, huge changes that were really detrimental, and then that thing just died off and its genes never got passed along. But anyway, again, this is more evidence from homologies. You need to be very familiar with what homologies are. Specifically, because there's different types of homologies, and I'm going to get a little bit more specific and tell you the type of homologies we've been talking about are called homologous structures. So again, for the exam, you need to know these different types of homologies And right now, so far, I'm telling you, every one I've told you about so far, that's called homologous structures. So there we're talking about, physically, right? The features that have different functions, but are structurally similar because of common ancestry. And when we get back on Friday, then we'll talk about the other types of homologies. But for now, that's where we'll end it. That's it. Send in those words before 9 a.m. Don't forget one question about the material covered in this lecture. And I'll see you at 9, unless you've already done the lab, in which case you don't need to be here.